way that your assumptions could be violated is if you have correlated errors. And unfortunately for correlated errors, there's really not a single check for this because there are just so many different ways that errors can be correlated. But I'm going to talk about a couple just so that you can sort of get a sense for what I mean by correlated errors so you know what to look out for. And often the solution is really that you need to fit a more complex model. So you need to sort of take into account the structure of the data when you're fitting the model. And so three kind of common examples are when data is collected over time. And so for this, if you have some time series data, for example, there are advanced techniques to be able to account for the correlation between time points that you would expect. Another common example for correlated errors would be if you have spatial data. And so if you have data that's collected kind of over space, that is also going to be correlated. So for example, if you were trying to look at how different trends occur across the United States, you might expect kind of counties that are right next to each other to have similar values as opposed to counties that are really far away. And so you'd want to be accounting for that correlation. And then finally, data generally collected in blocks. A really common example for sort of some correlated data that you might have is when you, if a study happened that was looking, for example, at how some treatment might affect your eyes. And let's say you enroll 30 people into your study, but you use this treatment on both of their eyes. And so you use the treatment on the left eye and the right eye. And in general, this is not always true, but in general, you would expect that, the treatment in the right eye would be similar to the treatment in the left eye, like the way that kind of behaves within each individual. And so basically you'd expect there to be some correlation between the two eyes for a single individual. And if you don't account for that, then you'll end up getting the wrong confidence intervals. And so that's just a common example of another type of correlated error that's possible. And so in all these cases, the way you basically think about this is sort of what is the structure of my data, and is there some underlying correlation that we would expect that we need to account for? And typically, linear regression or least squares, as we've learned it so far, is not going to necessarily be the answer if you're trying to do hypothesis testing or calculate accurate confidence intervals if you're in one of these circumstances, but there are ways to fix this. And so let's talk now about just solving these problems in general. So the first problem we've talked about is constant variance. And so this can sometimes be resolved by fitting your model differently. So perhaps by incorporating transformations. For example, you could try to take the log of the outcome y. That's kind of a common transformation that's used when you see some fanning or some non-constant variance. Another fix is weighted least squares. And if we have time, we're going to get into sort of how you can actually do this in practice. All right, normality. So when the normality assumption is violated, it turns out that we can actually appeal to the central limit theorem. If you have a large enough data set, we really don't have to worry as much about normality because our confidence intervals will actually be approximately correct. So this is the first thing is, if you notice normality assumptions being violated, perhaps you can either get some more data or if you have a lot of data and it's really not wildly violated, then perhaps things will just be okay because the central limit theorem will kind of take care of it on its own. But if you're still worried about it or you have a small enough sample where it's maybe still a problem, for skewed distributions, transformations can help. For example, when you looked at kind of the log normal, that probably looked a lot like one of the skewed distributions that you had looked at in the application exercise. And so that can sort of give you some sense that maybe there's just a transformation that you need to be doing in order to sort of help solve this problem. But it's important to check for the constant variance and linearity assumptions first, because oftentimes if you check for those and find a way to fix them, and we're going to talk a little bit more about linearity in just a couple minutes, but if you find a way to sort of fix the constant variance or the linearity assumptions, a lot of times by the time you get to checking normality, those issues might be solved as well by whatever you did to solve the constant variance or linearity problems. So again, these are problems when you're trying to use hypothesis testing or confidence intervals. And for normality in particular, because we have the central limit theorem, we do rely on not needing to be as worried about this kind of as our sample size gets bigger. All right, correlated errors. So I sort of alluded to this, but essentially you need to update the structure of your model, which sometimes means you need to fit a more sophisticated model. One type of model that can help in certain circumstances is a generalized least squares model, and if we have time, we'll also talk about that. So we'll talk about weighted least squares and generalized least squares if we have time within this class.